This is Lesson 3. Lesson 3 starts in the same notes packet with, this time, Roman numeral 4, miscellaneous substitutions. What we're looking for here are integrals that have the nth root of some function, f of x, and some strategies of how to deal with those. There are really two main strategies, and I'll write them as A and B. So the first strategy is to let u equal the nth root of f of x, and the other strategy, B, would be to let u equal just f of x. Now what we'll do is we'll run through the examples using both A and B to see how they are similar and different. Example number 1 from the notes. Example number 1 is the integral x cubed over the cubed root of x squared plus 4, and of course dx. Okay, to do this problem first, we're going to start with the A version. So if we're doing the A version, then we're going to let u equal, see we have a radical in the denominator, and so we're going to let u equal the cubed root of x squared plus 4. So the strategy here is once you have selected your u, the idea is to get rid of the radical. So to get rid of the radical, I'm going to cube both sides. So u cubed is equal to x squared plus 4. And then what we also want to do is solve for the x version of it. So x squared equals u cubed minus 4. Now we do not want to take the square root because the goal was to get rid of the radical to begin with. While we're at this step, it makes sense to find dx in terms of du. So here we have 2x dx equals 3u squared du. And that's going to become an important element to this integration. Okay, so back to the integration. So looking at this, we have an x cubed. I don't have an equation for x cubed yet, but I could write this as x squared times x dx over the cubed root of x squared plus 4. Okay, so now what we're going to do is a bunch of fancy substitution. In the numerator, instead of the x squared expression, we're going to write u cubed minus 4, which was the substitution made from this. And then x dx, well, if I want x dx, I'll come down here and that'll be 3 halves u squared du. I solve for x dx. So x dx is equal to 3 halves u squared du. And the denominator then becomes simply u. That's basically the trick. After we simplify here, we're going to have 3 halves u to the 4th minus 6u du. And that is as easy as they come, simple antiderivative. So we have, let's see, 3/10 u to the 5th minus 3u squared plus c, and that's going to come out to be 3/10. Back sub now to make it in terms of x. So this is going to be x squared plus 4 to the power of 5 over 3, because u is equal to the cube root of that quantity, minus 3 times the quantity x squared plus 4 to the power of 2/3 plus c. So there you go. Now there is another way to express this, but I'll wait until we do it with B, and then we'll show how you can make both answers look the same. Okay, so looking at part B, the difference here is what we're going to let u equal to different strategies should come out to be the same result. Here we're going to let u equal the radicand, x squared plus 4. But we're going to continue in the same process. U minus 4 equals x squared. Again, we got rid of we don't want to introduce any new radicals, so we're going to leave it like that. And then du equals 2x dx. So let's take a look at how this looks when we substitute it. Okay, we're going to start off by saying x cubed is going to be x squared times x dx. So you can see I'm going to pull out a 1/2 here. Then we're going to have x squared over cubed root of x squared plus 4 du. I guess that's kind of annoying. I just wanted to show that I got rid of an x by solving for dx and brought out the 1/2. Anyway, let's continue. So now we have 1/2, the integral. X squared, we know from above, is u minus 4 from here. And we still have a du. And then in the denominator, that's going to be u to the 1/3 power. So continuing along here, it's 1/2, the integral. Now I'm going to take this denominator and divide into both terms so that I have u to the 2/3 now minus 4u to the negative 1/3, and that's du. Okay, again, simple antiderivative now, so 3/10 u to the 5/3 minus 3 u to the 2/3 plus c, which then equals 3/10 u to the 2/3 times u minus 10 plus c. Then that comes out to be 3/10 x squared plus 4 to the 2/3 times x squared minus 6, because the plus 4 minus 10 gives you the minus 6 plus c. That's actually also the form that the calculator would give, so this sort of begs the question, how would I make the item above in A look like that? So if you factored out let's write this 10/3, if you factored out x squared plus 4, if you factor out a 2 to the 2/3 power, then what we have remaining is an x squared minus 6. Again, that's a x squared plus 4 minus 10, gives you this net result, and now they look the same. You don't have to make it look the same, but just for your information. Moving on to example number 2. This one's a little different because we have two different radical expressions. We have x to the 1/2 and we have x to the 1/3. The idea is to let u equal x to the 1 over n, where n is the least common denominator. So can you tell me what n would be if it was the least common denominator of the 1/2 and the 1/3? I hope you can say that n is equal to 6. So that means we're going to let u equal x to the 1/6. Now you're going to see why that works in a moment. Do you know what to do from here? That's our strategy. Once you have u, we solve for x. X equals u to the 6th, and then we find du in terms of dx. So 6u to the 5th du equals dx. These all become important players in our substitution. Let's take a look at this. If I have x to the 1/2, and I want that in terms of u, then this is going to be u to the 6th to the 1/2, which equals u to the 3rd. Likewise, x to the 1/3 is going to be u to the 6th, that's coming from here, u to the 6th to the 1/3, which then becomes u squared. So if we make our substitution, I'll come down here for the substitution from here to here, then dx we learned is 6u to the 5th du. The square root of x becomes u cubed, and the cubed root becomes u squared. So there's our initial substitution. I'm just going to simplify a little bit here. we have u to the third if I divide top and bottom by u squared. Then we have this expression. You should actually be able to integrate at this point. I'm not sure how comfortable you are with this problem. Maybe press pause and see if you can figure it out. This one's interesting because the power in the denominator is larger than the power in the power in the numerator is larger than the power in the denominator. So this is going to involve a little bit of long division. How exciting. So we would have to take u cubed divided by u plus 1. Now I'm going to put some dummy variables in here. 0u squared plus 0u plus 0, I guess, or nothing. So how many times does u plus 1 go into u cubed? That would be u squared. So then it's u cubed plus u squared, from which I would subtract. This is just good old-fashioned long division. So negative u squared plus 0u. That would go in negative u times. So we have negative u squared minus u, from which I subtract. That's going to give me a positive u. And that goes in one time. So we have u plus 1, from which I subtract. That's going to give me a negative 1. That's the remainder. So when I take this division, I get u squared minus u plus 1 with a remainder of 1, which goes over the divisor like that. So this is a little bit messy. Let's see if I can't come down here for the integration. And we have 6 times u squared minus u plus 1 minus 1 over u plus 1, all of that times du. So that simplifies kind of nicely. That comes out to be 6u cubed over 2. I'm doing the integration and distribution at the same time. 6u squared over 2 plus 6u minus 6 natural log absolute value of u plus 1 plus c. And of course now we have to put this back in terms of x. So 2 x to the 1/2 minus 3 x to the 1/3 plus 6 x to the 1/6 minus 6 natural log absolute value x to the 1/6 plus 1 plus c. That's the end of part 1 of lesson 3.